Yeah, thanks for the introduction. My name is Julian. I'm a PhD candidate at the University of Basel in Switzerland in a quantum theory group. And today I'm going to present you a differentiable implementation of isospectral flows for matrix diagonalization, which is joint collaboration with the with the Julia lab here at MIT. So a key problem in numerical analysis is the design of stable and efficient algorithms for solving eigenvalue problems, so for finding eigenvalues and corresponding eigenvectors. And in this talk, we're going to focus on the diagonalization of Hermitian matrices. And for Hermitian matrices, this essentially boils down to applying an appropriate unitary transformation U, such that after the application, we end up with the correct diagonal matrix. Now, typically, we perform this transformation in an iterative fashion, and here L denotes this flow parameter, which labels each of the iterations. And what we want is that as this iteration number L goes to infinity, we end up with the correct diagonalized Hermitian matrix. Now, traditional methods such as Jacobi's algorithm or QR algorithm perform this transformation in discrete steps. So here L is an integer number. Now, if we take the continuous limit, so we let L be an element of the positive reals, we end up with what's called isospectral flows. And here isospectrality refers to the property that the spectrum is the same, so the matrices have the same eigenvalues throughout this flow. Now, an isospectral flow is governed by the following ODE. So here we see that this Hermitian matrix H evolves according to an ordinary differential equation with respect to this flow parameter L. And on the right-hand side, we have the commutator between what's called an anti-Hermitian generator and the Hermitian matrix H. And in principle, we are free to choose this generator eta however we like, as long as it's anti-Hermitian. This will result in an isospectral flow. But in general, we only know two classes of generators which have provable convergence, so for which we know that if we let this flow go towards L, we let L go to infinity, so we solve the ODE towards its steady state, we end up with the correct diagonal matrix. And these two classes differ in how the off-diagonal elements evolve over the flow. So on one class, the norm, the L2 norm of these off-diagonal elements is going to decrease monotonically over the flow. An example of this is what's called the Wigner generator. So here you see the matrix elements of this Wigner generator eta, and note that it also depends again on this Hermitian matrix. And the second class, and there in the second class, the off-diagonal elements are also allowed to temporarily increase. An example of that is called the Toda generator. Now, in general, different flows induced by different generators also have different properties, such as stiffness, or they differ in the number or nature of the fixed points, or how they preserve different sparsity patterns. So as an example, let's consider this 2x2 real symmetric matrix, which has essentially two parameters, which is the W on the diagonal and omega on the off-diagonal. And here you see the phase portrait for the Wigner flow, so the flow induced by the Wigner generator on the left and the Toda flow on the right. And you see that in both cases, the phase portrait, or all of the trajectories in this phase portrait have this circular shape, which comes from the fact that this flow really happens on an isospectral manifold. So it's analogous to rotations in complex space. And you also see that they differ in their fixed points. So in green, you see the line of stable fixed points, and in red, the line of unstable fixed points. And if we now pick sort of an initial Hermitian matrix, so initial values of W and omega, and let this flow run, we see that it evolves towards this line of stable fixed points where omega is equal to 0. So the off-diagonal elements are 0, and we end up with the correct diagonal matrix. Now, for a given initial matrix H, we can solve this flow using ordinary diffq. Note, however, that standard ODE solvers do not preserve isospectrality. And so it's better to use geometric integrators. So you might be familiar with a special case of a geometric integrator, which are symplectic integrators, and those respect energy conservation. And in our case, we are concerned with conserving the eigenvalues or the spectrum. Now, isospectral flows take up a special role in quantum physics. So the properties of closed quantum systems are described by Hamiltonians. So Hamiltonian is simply a Hermitian matrix whose dimension, or square Hermitian matrix, whose dimension grows exponentially with the number of constituents. And these continuous isospectral flows allow one to, in a very elegant way, introduce approximations which enables the analysis of larger systems. So I don't have time to go into the details, but I just want to sketch the key idea, which is that one expands the Hamiltonian in a suitable operator basis and then truncates this expansion and simply flows the remaining coefficients. So here I'm showing you this for the example of a qubit. So the qubit is described by, now it's a Hamiltonian, the same matrix you've seen before. And here we can do an exact expansion, so we don't have to introduce any truncation error. And we can expand it in terms of Pauli matrices, sigma c and sigma x. And then if we, here the two parameters are this w and omega. And once we plug this Hamiltonian into the commutator with the Wigner generator, we can derive these two differential equations which cover the evolution of these expansion coefficients. And if we solve these differential equations towards their steady state, so for L going to infinity, we can plug those values back in and end up with the diagonal Hamiltonian. So that's the general procedure of applying this method. Now, if we introduce these approximations and flow these coefficients, that will lead to some restrictions. In particular, we cannot access the eigenstates anymore because we are sort of restricted to this reduced subspace, and as soon as we leave it, this computation becomes intractable. But there are still a number of forward problems which are compatible with this procedure. Namely, we can still calculate all of the energy eigenvalues, and more generally, we can calculate expected values of physical observables in eigenstates or thermal states, as well as time-dependent expected values. And now, differentiable implementation could, based on these forward problems, enable a number of interesting tasks. For example, we could compute differential physical quantities, we could perform parameter estimation, inverse Hamiltonian design, or it would allow us to seamlessly integrate this isospectral flow method into other scientific workflows, such as the design of quantum controllers. Now, how does one differentiate an isospectral flow? So there are different ways to go about it. Sort of at the most basic level, we could just view this isospectral flow as a generic Julia program and directly apply automatic differentiation on the base operations. So in our case, the operations of the differential equation solver. But if we put in a bit more structure of our problem, so for example, by noticing that we are solving a system of ordinary differential equations, we could use the continuous sensitivity analysis algorithms embedded in SciML sensitivity.gl. And if we go even further and put more structure into the problem, we can do this by defining custom forward and adjoint rules, which is made really easy with chainrules.jl. And there we sort of take two different routes. So one is based on applying the implicit function theorem on the steady state condition. So recall that in the end, we're only interested in taking derivatives with respect to the diagonal matrix, which corresponds to the steady state, and not really about the derivative at intermediate stages during the flow. But here in this isospectral flow method, we have an additional constraint that ensures isospectrality, and that's why the steady state rule, which is implemented in SciML sensitivity, doesn't work out of the box. Then a second approach would be based on formulating the eigenvalue problem and applying perturbation theory. And in this case, we have to be careful not to include any computations which involve the eigenstates. So we know that we don't have access to the eigenstates, or else if we do, then it's going to be intractable. So we have to formulate this method in a way which deals or only uses this limited information we have when flowing the expansion coefficient. So if we do these approximations. Yeah. So as a toy example, we can again consider our qubit, and for example, we can compute the differential physical quantity, which is the specific heat, which corresponds to the second derivative of the free energy with respect to the temperature. Another example would be to perform inverse Hamiltonian design. So here we optimize the expected value of the magnetization in the ground state as a function of the external field strength omega using gradient-based optimization. Yeah, with that, I'm at the end, and as an outlook, we are currently working on applications to large quantum many-body systems and performing benchmarks. Thanks.